Point. Okay, so hi everyone. So this is a joint work with Judy, Chakraborty, Dennis Hoffines, and Willy Maurer. At least the part for this year's recruit. Okay, so let's start. Let's start with some motivation. So there are two basic guarantees that secure messaging applications should give, which are confidentiality and authenticity. And because we tend to have very long-lasting sessions in our phones, there is an increased chance that our phones get compromised. So current messaging applications also try to guarantee things like forward secrecy and backward secrecy. Just one thing, feel free to interrupt me at any time if you have questions. Okay, so forward secrecy just gives the guarantee that if everyone participating in a chat wants to delete the chat history, then they can do this. Even if like an adversary captures ciphertexts and later on corrupts this party, any part in the chat, they cannot decrypt them. And backward secrecy just guarantees that even after someone's phone gets compromised, it's still possible to recover security guarantees like confidentiality. Okay, so, but now there are a few questions. First, what if some parties want to keep a chat history? Well, in this case, actually, forward secrecy gives no guarantee. And what if some parties are even dishonest? And in this case, neither of these guarantees gives, well, any guarantee. So then the question is, what can we hope for in these cases? And essentially, there are two things we can hope for. One of them is called off-the-record deniability. By the way, can you see the entire screen? Because, okay, no, it's... anyway, one of the things is off-the-record deniability. So consider that there are like two parties who are chatting with each other. There is Buggles and Video. So Buggles is dishonest and is the owner of the phone you see here. And Video is honest and is a killer. There is also another party who is not in the chat, who is Judy. And Judy is dishonest and is a judge. Just one thing, which is Judy and Buggles are not colluding. So in particular, Judy does not trust Buggles. So what if now Buggles tries to convince Judy that Video killed a radio star? Like, Buggles could try to cooperate with Judy, could try to convince Judy. It could give its secret keys, everything that it can. And off-the-record deniability guarantees exactly that Buggles should not be able to convince Judy. Okay, the other guarantee is consistency. So now imagine that Video creates like a chat group called Killer Confession with three parties, Buggles, Video, and Grace. This time, Buggles is honest and Video is dishonest. And Grace is another part in this group and is just honest and is an inspector who is looking for Radio Star's killer. Okay, so then one thing that Video could do is to try to frame Buggles by just sending malformed ciphertexts that decrypt differently in Buggles and Grace's phones, so that if Buggles would reply to it, maybe it would look very suspicious. For example, the following could happen. So this is the same setting that I was just telling you. There's this group shot, and in the left, there is Buggles' phone. And in the right, in the slide mode, there is Grace's phone. So Video came up with some ciphertext that it decrypted differently in, in Buggles' phone and in Grace's phone. When I say decrypted differently, it could also be that it decrypted in one phone, but not in the other. And it just sends like two ciphertexts, one that it decrypts in Buggles' phone, but not in Grace's, and the other one decrypts in Grace's, but not in Buggles'. And then, of course, this answer by Buggles looks very suspicious in Grace's phone. Okay, so the thing is that there is a type of scheme that captures these basic guarantees, confidentiality, authenticity, but also off the record and consistency that we just saw. And there is another guarantee, which is anonymity, that it also guarantees. So anonymity is also useful for secure messaging, but I'm not going to explain why, and unless you're really curious. In that case, we can go over why, but later on the presentation.
So I have a question.
Yes.
So
yes.
Off the record and consistency, they seem like some conflicting requirements, do they? Or
yes, that's a great question. So they're not conflicting. Let me go back. So the thing is that off the record is a guarantee given to the sender, right? So we want to guarantee to the sender that it cannot, that a receiver will not convince someone else that the sender sent something. And consistency is actually about giving a guarantee to the receivers that the sender cannot like fool them. But yeah, does this answer your question? Or
yeah, sort of, yeah.
Okay, we'll go more into detail, and I hope that it becomes more clear. For now, it's very fluffy version, and then it will be slightly not very formal, but I hope we can, yeah, sufficiently formal. Okay. So yeah, there are these schemes that give these 5 guarantees, and what? Right. And now let's have a closer look at off-the-record deniability. So in the setting that I was telling you, Buggles was dishonest and was trying to convince Judy, but we also don't want Judy to be convinced in case Buggles is honest. So suppose that there was another party just maybe peeked at Buggles' phone and then tries to tell on video to Judy. We still don't want Judy to be convinced that Buggles sent this message. Okay. So to summarize, if Buggles is honest, Judy only knows public information in prior work. And if Buggles is dishonest, then Judy will know public information plus Buggles' secret keys because Buggles cooperates with Judy. So the question is, what if Judy could now get more secret keys? Like maybe it could get the signer's secret keys because the signer is under suspicion. And this is the setting we consider in this work. So in case Buggles is honest, Judy will know public information, but now also video secret keys. And if Buggles is dishonest, then Judy will know public information and all the secret keys. So Buggles secret keys and video secret keys. Okay. Another important issue that is particularly important for MDRS-PKE schemes because they have applications to messaging is scalability. And very informally, we consider 2 types of scalability. One of them is security scalability, in the sense of having tight reductions to standard assumptions. And the other one is in terms of efficiency. So we want, if you have a group size, if you have a chat group with N participants, we want the ciphertext size, encryption, and decryption time to be at most linear in N. Actually, there are also lower bounds that essentially say that the best you can hope for is linear in the number of receivers. So, but I'm not going to explain this why, but they're actually simple. Yeah. So the thing is that in prior work, what we have, so first, security reductions are non-tight. In particular, it degrades with the number of users. And for a group chat with N participants, the current constructions only achieve ciphertext size, encryption, decryption time that grow quadratically with the number of receivers. Okay, so what we do is just we give the first scalable in every sense. So it's independent of the number of users and messages, security, and ciphertext size, encryption, and decryption time only grow linearly with the number of receivers. Okay, so now I'm going to give a more careful overview, although not formal, of these MDRS-PKE schemes, their syntax and security notions. And then we'll see how to construct one from 2 primitives that I will, from 2 primitives that most likely you're not so familiar with, because one of them I introduced in one of the papers, and it's not really. And the other one is MDVS schemes. But the goal, yes.
Question. So this MDRS-PKE, does it handle the authentication when signing keys or videos leak, or is it just the more?
Oh, no. So you if the signer key leaks, you cannot get authenticity. So the thing is that that's a great question. So the thing is that we see the judge as a passive party. Like the judge is only there to try to decide something, but it would not try to get the secret key of a signer and then impersonate the signer, because then there is like there is nothing you can hope for, because there is no secret somehow.
Okay.
So the judge is only there just to decide, like you give it all information that you can, and it just tries to say, well, was this, did the sender really send this or not? And ideally it cannot tell that. But authenticity is not defined with this judge. So when you define authenticity, it's, yeah, you just do not get the secret key of the judge or of the sender. The judge does not get the secret key of the sender.
Okay, thanks.
Okay, yeah. Thank you for the question. That was actually a very good question. Okay, so let's just have a brief look at these MDRS-PKE schemes. So here we have 3 senders. Some are honest and some are dishonest, and we have 5 receivers. SPK just stands for sender public key, and similar for SSK, and RPK is for receiver public key, and so on. Okay, so when someone wants to send some message, what it does is, in this case A2, it uses its secret key, and it will encrypt with respect to this vector of public keys of the receivers some message. What about decryption? So decryption, one thing I want to highlight is that it only needs the secret key of the receiver. So the receiver does not need to know who the sender is, and does not need to know who the other receivers are. It really only needs to know its own secret key. So it will essentially obtain back everything that that the sender used for encryption. The only thing that it does not obtain is the secret key of the sender, but it gets the public key of the sender. Okay. So the 5 notions that we consider are these, and there is one thing that I'm going to assume, which is that every party's key pair is honestly generated. Okay. So confidentiality captures that if the sender is honest and if it's encrypting something to 2 honest receivers, then parties who are not the receivers will not learn anything about the contents of the message. And in this case, Judy can even get the secret key of the sender and will still not know what is being sent by this A3. This is some in CCA2 type of notion. Then there is authenticity. And authenticity says the following. So dishonest parties cannot come up with a ciphertext. And as you were saying here, notice that Judy is not playing anything here. I mean, it's just here because it was also in the previous figure, but here it just does not do anything in the game. So the thing is that in this case, of course, the secret key of honest signers do not leak, otherwise you cannot get anything. And authenticity guarantees that dishonest parties cannot come up with some ciphertext that when an honest party decrypts it, then it could obtain, you know, some sender public key, vector of receiver public keys and message, but either the ciphertext they come up with decrypts to something where this does not correspond to anyone's public key. By the way, do you see the cursor?
Yes.
Okay, great. Or if it is someone's sender public key, then whoever it is, then this part is signed this message before, encrypted this message before. So this is like this UFCMA for signatures, slightly different, but it's along those lines. Okay, so what about off the record? So off the record is actually for any subset of the receivers. What does this mean? That any subset of the receivers who is dishonest can forge ciphertexts that look like the real signatures or ciphertexts. Okay, so imagine that A3 sends this message M to B4, B5, B2. And now B5, who is dishonest, decrypts it and obtains its information back. And tries to convince Judy that, that A3 sent this message to these three parties and can also leak his secret key. So the thing is that off the record guarantees that B5 cannot do this. How does it guarantee this? Well, because maybe A3 never sent anything, maybe it was all forged by B5. And so in this case, even if Judy gets the secret key of the signer of the signer A3, it should not be able to distinguish if it is a real signature or if it is a forged one. Okay, let me know if you have any questions. Otherwise, yeah, we can continue. So the thing is that any subset can forge, including the empty subset. What this means, the empty subset, is that someone else comes up with a forged ciphertext. So someone who is not any of these receivers and who is not the signer, of course, would come up with something using only public information. And this forgery takes as input the secret key of every dishonest receiver. Then there is consistency. And consistency says the following, yes. Okay, says the following. So if A1, in this case, a dishonest party comes up with some ciphertext, and suppose now that B1 decrypts this ciphertext using its secret key and obtains this sender public key and this vector of receiver public keys and this message M. So consistency says, look, everyone whose public key is here. So if B1 decrypts and obtains this vector of public keys, for every honest receiver whose public key is in this vector, if they try to decrypt this ciphertext, they have to obtain exactly the same. So in this case, B4's public key is in this vector, so it also has to obtain exactly the same. Okay. And anonymity is, somewhat similar to confidentiality, except that it's not the message that the adversary does not learn, but this time it's who the receivers are. It learns who the number of receivers, but not who they are. Also, in this case, it also does not learn who the sender is. Okay, so this was just an overview of the security notions. Now I'm going to explain you at a very high level how to construct such a scheme from two building blocks. Actually, the construction is super simple. And I'm going to show you the exact construction. And I am aware that I did not yet tell you the guarantees of these building blocks, but I will cover at least the ones of this MDVS scheme later on. Okay. I think it will be clear anyway. So the main idea is to use this MDVS, which is a type of signature scheme, to sign the receiver's PKE-BC public keys and the message, and then to encrypt under this PKE-BC scheme, which is some sort of PKE type of scheme, all the information that is needed to verify the signature, the message, and the signature itself. So it will encrypt all the public keys of the sender and of the receivers, the message, and the signature. So the final ciphertext is just this PKE-BC ciphertext. But we can look at this a bit more formally. So the scheme is real simple, otherwise I would not be showing this. So you will have a setup. The setup of this MDVS scheme and of the PKE-BC scheme. Then the sender's key pair is just the MDVS key pair. And the receiver's key pair will be an MDVS key pair and a PKE-BC key pair. Okay. So to encrypt, this looks scarier than it actually is. So to encrypt, what we do is the following. So we're going to sign, as I was telling you, the vector of MDVS public keys. The vector of PKE-BC public keys and the message. And they're going to encrypt all the information. So the sender public key, this vector of MDVS public keys, the message and the signature, under this vector of PKE-BC public keys. Okay, to forge a signature, let me just say something, which is each of these RSKs. Well, actually, never mind. I can go over this afterwards. Does not matter right now. So to forge a signature, all you have to do is to forge an MDVS signature. And then the public key part is, well, does not really need any secrets. So you just generate a ciphertext of this PKE-BC. So it looks very much like a normal encryption. Okay. What about decryption? So to decrypt, the first thing you do is you just decrypt the ciphertext, PKE-BC ciphertext, to obtain everything that you had. So the signer public key, this vector, V, the message and the signature. And if everything looks fine, you'll just verify if the signature is valid for the information that was decrypted. And if it is, you will output this signer public key, the vector V, and the message M. Okay. So why was I telling you this? It was just so that now we can understand what we need in order, for example, to make sure that the scheme is scalable in terms of security and also in terms of ciphertext size, encryption, and decryption time. So the first thing that we need to make sure is that the security reductions from this MDRS-PKE scheme to the PKE-BC and to the MDVS schemes are tight. And actually they are. The second thing we need is that there is a PKE-BC scheme with tight security reductions to standard assumptions, and this we also have. And the third thing is that we need an MDVS scheme which is tightly secure under standard assumptions, but this is the first problem we'll have to solve. Okay, regarding efficiency, so consider some message sent to end receivers. There is already an MDVS scheme which achieves signature size, signing time, and verifying time, which are linear in the number of receivers, but there is no PKE-BC scheme that achieves linear sized ciphertexts. So this is the second problem we solve in the paper, but I'm most likely not going to cover this in this presentation. Okay. So what we do is we just give the first tightly secure MDVS scheme to standard assumptions. And the construction is actually conceptually simple. And we also give the first efficient PKE-BC scheme, also tightly secure under standard assumptions. And both schemes are actually proven tightly secure under adaptive corruptions. Okay, so now let's actually see how to construct an MDVS scheme. So the MDVS scheme, first of all, is going to have to satisfy three notions. It is authenticity, off the record, and consistency. So before that, actually, let's look at a very much simpler case, which already is going to capture the main ideas, which is a DVS. So for a single verifier, it only has to satisfy authenticity and off the record. So let's see. So the syntax for a DVS scheme is somewhat similar to this MDRS-PKE. So to sign, a signer uses its secret key and the verifier public key of the receiver and signs some message M. To verify, the verifier will have to use all this information. So it will have to use this secret key, also the sender's public key, the message and the signature that it received. Okay, so authenticity just says that, dishonest parties should not be able to come together and forge a signature on a message that was never signed by an honest signer to an honest verifier. And finally, off the record, again, just says that this A3 will not, that this B5, dishonest receiver, will not convince anyone, will not convince Judy that A3 sent anything because it could have also forged a signature. So let me know if you have questions about these notions, because next I'm going to actually construct something satisfying this at the high level. But okay, so let's very brief recap, just one slide thing. Sorry. Right. So in authenticity, the adversary gets absolutely no secret key, not of the sender, not of the verifier. And the goal is that it cannot forge signatures on unsigned messages. For off the record, there are two cases. If the verifier is dishonest, then real signatures should look exactly like dishonest verifier forgeries. And in this case, adversary gets all the secret keys. And in case the verifier is honest, real signatures should look just like publicly computable forgeries, even to Judy, who gets the signer's secret key. Okay, so let's get the first construction. As building blocks, we will use an IP scheme and a public key encryption scheme. So what is the signer key pair is going to be just an IP key pair. A verifier key pair will be also an IP key pair, but also PKE key pair. Okay. And what is the goal here? So the signer is going to compute an IP shared key with the verifier, and then it's going to encrypt this under the verifier's public key. So if you think about it, if no one knows the signer's secret key, nor the verifier's secret key, then no one can forge a signature because the verifier can just verify by checking, by decrypting the ciphertext, and then recomputing this Nike key to see if it matches. So we have authenticity. And on the other hand, if no party is dishonest, so for off the record, in case all parties are honest, then we also guarantee that Judy will not distinguish real signatures from forged ones because they are encrypted under the verifier's public key. And in case the verifier is honest, Judy will not get verifier's secret key. The last case is, what if the verifier is dishonest? Well, in this case, actually, the verifier can also just compute ciphertexts that have exactly the same distribution as the signer, so we are also fine in this case. Okay, so let me know if you have any questions until now, because if you understand this part, yes.
So these Nike and this PKE scheme, do they have to satisfy any further property? Like you said.
No. I mean, I'm not saying exactly what properties they have to satisfy here, but for example, if you would take CCA secure PKE scheme,
okay,
and an IP key satisfying like some notion just guaranteeing that you cannot compute the shared key between two parties, this would be sufficient.
Okay.
So actually in our construction, we do not need CCA secure PKE scheme. We'll just use CPA secure, but it is not too important, to be honest. Not to get an idea, at least.
Yeah, makes sense.
Okay. Okay, great. So the problem now is that actually there is, or it is unknown if there is any tightly secure IP scheme under standard assumptions. And so we have to solve this. Okay. So essentially we have to get rid of the Nike. Yes.
Why is this the problem? Like what the Diffie-Hellman key exchange, for example, why is it not tight?
So to be honest, I'm not the expert in this, but what I can tell you is the following. Think about how you could try to prove security in a tight way if some parties can be corrupted. You have to choose where do I embed the challenge. So actually there are papers proving like trade-offs between key sizes and security and things like this. And at least as far as I know, there is no tightly secure Nike scheme, but I'm not really an expert in this, like
So
not at all actually. Yes.
What the number of Nikes you make with different parties? Like what is the
Sorry, can you repeat?
What is the tightness parameter?
Aha, yes. So the problem is number of users.
Okay.
It decreases with the number of users.
Okay, thanks.
No problem. Yeah. Sorry that I'm no expert in this thingy. Yeah. Okay, so we have to solve this. And how do we solve this? Well, essentially, we do not use Nike. And actually, the main thing is let's try to understand what is the role of the Nike. What do we need this Nike for? Well, on one hand, it's giving us authenticity because this key shared is only computable if you have either the signer secret key or the verifier secret key. On the other hand, it's giving us this off the record because in particular, in the case where the verifier is dishonest, it can compute or it can forge signatures by also computing this shared key. So if you think about it, what this Nike is really doing here is kind of proving an or statement. It's proving that either the signer really signed this message M or the verifier forged a signature on this message M. Okay, so now with this in mind, let's try to come up with a scheme which is actually tightly secure, or a scheme based on primitives from which tightly secure instantiations are known. Okay. So the building blocks for our scheme are actually very simple. So we'll use just a one-way function, a PKE scheme, and an ISK. And we'll have this setup. So the setup will be just the CRS for the ISK plus a public key that is honestly sampled for this PKE scheme. And then for the sender, signer or verifier key pairs, this looks very much like before, except that this Nike key pair is replaced by the pre-image and the corresponding image of this one-way function. So the signer's key pair is just the pre-image of one-way function, and the image of this one-way function, the corresponding image, and the verifier is also a pair like this, but also plus a PKE key pair. So let me tell you how a signature looks like. Right, just one thing. So I'm going to completely ignore the CRS because the notation is going to be already a bit, I mean, hope not too much, but this just tries to, yeah, keep slides a bit cleaner. Okay, so what do you do to sign? It's actually very simple. So you're going to encrypt under the verifier's public key, this bit 1, okay? You can imagine this bit 1 as just saying, look, for this verifier who owns this public key, it's the signature is essentially going to verify. It's not really like this, but you can interpret it for now like this. And then you encrypt under this public parameter's public key some more information. So encrypt the message, the same bit 1, and the signer's secret key. Okay, so this pre-image. And then you're going to prove that this pair, this CCPP, a bit informally, but you're going to prove that this is in some language. And this language is what is going to give us the guarantees that we need, essentially. Okay, and the output will just be this NIST proof, the C, and the CPP. What about verification? So verification, what you do is you're going to first check if these ciphertexts are well formed, like if this belongs to the language that it should belong to. And then you're going to decrypt this bit using the verifier secret key. You're going to output the end of the two things. Okay. So now the question is, what should this language guarantee? So this is just slightly more formal. This is the actual tuple that we're going to require to be in the language. And what we want it to guarantee is that if the sigma is a valid signature, then the CPP encrypts one of the secret keys. So in other words, a bit more, if this C for the receiver encrypted under the receiver's public key encrypts this bit 1, then the CPP must include one of the secrets and the message M. Okay, so one of the secrets of either the signer or of the verifier. Okay. Okay, so is this clear? Okay, I will assume so. If you have questions, please just let me know, really. Okay.
So,
yes.
oh, I was just wondering, like, this seems like a somewhat complicated statement. Did you have like a tailored construction in mind, or are you just not gonna try to instantiate this?
So to be honest, we did not try to instantiate this, but we did try to make this as simple as possible. But let me say something though, which is so somehow yeah, so we try to make the language as simple as possible. But I think there are some things we cannot really get away with. So the thing is that you could also try yeah, no, so the language you try to simplify it, but no, we did not think of concrete instantiations or how to implement it efficiently. We do hope that we can do this, but we do not know exactly how, but we do think that it is possible. But the thing is that I'm not the expert in this, and so I cannot really answer you like in a super satisfactory way.
Oh, no. Yeah, thanks.
Yeah.
You have a...
But yeah, but I do think that you can instantiate this using these sort of Sahai proofs. Yeah. Okay. So we try to make actually the languages to be as simple as possible, in particular to be an end of statements. Well, I'll tell you more about this later on, because for now it just yeah, it is not clear why I'm saying this. We are looking only at the single verifier case. Okay, but I hope this construction is clear to you. If it is, then let me just tell you the idea of this relation. So what we are going to do is the following. The relation is going to guarantee the following. So it's going to guarantee that this CPP and this C encrypt the same bit B, okay? And this is in the witness. And that the CPP encrypts this message M and this X here in the witness. Okay, so this MDVS match does not really give us anything, but we're actually taking an intersection. So we also need to look at the forgeability one. And the forgeability is doing what I had told you before. So if this bit B is 1, then the one-way function of this X, which is encrypted here under this public parameters public key, is going to be either the sender's public key or the verifier's image of this one-way function. Okay, so this was just a more formal way to tell you what I had told you before. Okay, so now what about forging signatures? So to forge a signature in case the verifier is dishonest, so in this case you actually get the verifier secret key, you're going to encrypt this bit 1 as before. The only difference actually is that when you're encrypting the CPP, you're going to use the verifier secret key and not the signer's secret key. Everything else looks exactly the same. What about a public forgery? So a public forgery is when you do not get the verifier secret key. Essentially, you're going now to encrypt this bit 0 because, well, anyway, the judge will not get the secret key of the verifier, so it cannot tell whether this is an encryption of a 0 or an encryption of a 1. And then, because this is an encryption of 0, we can encrypt whatever we want in the CPP. We do not have to encrypt any secret. So this is what we do. We just encrypt zeros. Okay?
Quick
Yes.
question. How do you generate the NISIC proof? Like, is this a satisfying witness?
Yes, it is. So this is a bit informal, but remember this witness, so vsk.x, right? And if we go back, look here, this x, we just wanted it to be either, like the f of x should be either the signer's public key or the verifier's public key.
Oh, I see. Okay.
Yeah, so the main thing is that, yeah, if the verifier is anyway honest, then we can take advantage of that because look, this is an implication, so we don't have to do anything in that case, essentially. Just have to encrypt this bit 0, and then the Judy cannot tell anything, right?
Yeah.
Okay. Okay, so it's good that this is clear because I know it's not so simple, but it's good that this is clear because then for the multi verifier case, the scheme is actually very similar. So the MDVS regarding syntax, only difference is that now you take more than one public key of verifiers, actually take a vector, right? And regarding forgeries, it's similar, but now we can, of course, try to forge for multiple verifiers. And the notion is essentially the same, but now with multiple verifiers. So one thing is that, you know, this not just that this is B3, B5, right? And here B5 is dishonest. And what we want to ensure is that this B3 will not be convinced, or because of authenticity, will not be convinced that this A3 actually signed something, even though one of the receivers, one of the verifiers is dishonest. Okay. Then there is also any subset of the record. This is similar to before. And yeah, now let's actually have a look at the scheme. So we'll have exactly the same setup, exactly the same building blocks, and the same signer skipper and verifier skipper. So now how do you sign? This looks scary, but it's actually not. So what do you do to sign? So for each party, you're going just to generate an encryption of a bit 1. So before I just generated 1 because it was one receiver. Now I generate 1 for each receiver. And then this is just notation, but for each receiver, we are going to have an alpha I. Essentially, if the receiver is dishonest, this alpha I would include the verifier secret key. But for a normal signature, this alpha I will include the signer secret key. And also this bit 1, which is the one that is encrypted for the verifier. So we're going to encrypt under this public parameters public key the message, ignore this one for now, and this alpha. Okay. So the bit from before, so the bit that we were encrypting for each party before is this. So this should match this. Okay, so then finally we're going to prove that this long tuple is in some MDVS language. What about forgery, or sorry, verification? Well, it's essentially the same as before. We're just going to check if this long tuple is in the MDVS language. And then you're going to check, okay, so which public key matches mine, and you're going to decrypt the ciphertext that is meant for you, like that is meant for the verifier. And you'll output the same again. So you'll output the end of this bit that you obtain and whether this tuple is in this language. Okay. So what about forgery? Forgery is essentially the same as before, but it looks more scary, but actually it is not. So what you do is, for each party, you're going to have to encrypt some bit. If this party, so if this party secret key is given as input to forge here, you're going to encrypt the party secret key and this bit 1. And otherwise, you're going to just encrypt zeros. And then you're going to encrypt the message M as before and this vector here. Okay, so then you're going to prove that this thing is in this language, and this is going to be your signature. Do you have questions about like this language? Sorry, about this scheme? Okay. Okay, I will assume not. So how does the language look like? Essentially, it is also similar to before. You're going to have a huge AND here. You're going to prove the following. So you're going to show that the CPP is an encryption of the message, this some bit B, and this vector alpha. And you're going to say, look, each ciphertext, each CI, is an encryption of this bit BI under some random codes. What about unforgeability? Forgeability is going to say that for everyone, if the bit encrypted for a party is 1, then either the eth_x, so this xi, is the, well, a pre-image of the signer's public key or a pre-image of the verifier's public key. This is maybe not so straightforward, but let me know if you have questions.
I think it makes sense, at least to me. But,
yeah. Okay, great.
Disjunction in the multi-receiver case.
Yes, exactly. Yes, yes. Great. Okay, so there is one more thing I haven't told you about yet, which is about consistency. But let's just try to understand consistency. So the thing is that the scheme is actually not going to change. There's one thing that's going to change, but it's the language. It's not the scheme itself. So what is consistency? Consistency guarantees us that a dishonest party cannot come up with some tuple, so some signers, some signer identity, some vector of verifier public keys, message and signature, such that one of the parties verifies, imagine that B1 verifies this as valid, but another party who is also an intended receiver will check that this is invalid. So consistency guarantees that if one party outputs some bit B as the decision of whether this is valid or not, then every other party will also, output exactly the same. So what does it mean? So it means that if you fix any signer at any vector of verifiers, message and signature, the honest parties in this vector will all agree on the validity of the signature, either all accept it or all reject it. Okay, so there is some bit that such that for every verifier, if they are honest, they will output this decision. They will output this bit B. as whether this signature is valid. How can we get this now? Well, this is the same as before. Okay, so this is exactly the same as before. I just highlighted something here. So we're going to use this bit as this bit B from here. Okay, so when you're signing the default bit, the default decision is going to be 1 here. When you are forging, the default bit is going to be 0. And now we have to change, or not to change, but to add something to this relation from before. So we're going to define another relation, this consistency relation. And the final relation for this MDVS will be the intersection of 3 relations. Okay, the 2 we saw before that I will recap next, and this one that I'm going to tell you now. So what does this relation say? So it says, look, for everyone, if this xi encrypted in this alpha I is not the verifier public key, is not the preimage of the verifier's public key. So if the verifier did not essentially participate to generate this one, then you're going to have to agree, this BI, you're going to have to agree on the same bit as everyone else, as every other honest party. This is like a default bit. Okay, so just summary. So these are the 3 things put together. You have already seen all of this. We have this MDVS match, MDVS and forge, and MDVS cons. So the new language or the new relation is just intersection of these 3 relations. Let me know if you have questions. I think I'm essentially finishing. I'm going to skip the PKE-VC scheme because otherwise it's just way too much. But let me know if you have questions until now.
So can you give some intuition for why this would give a tight security reduction?
Right. So the intuition is that you can, all the building blocks, you can instantiate. So the NISC, the one-way function, and the PKE scheme, there are tightly secure instantiations for these schemes, satisfying the security notions that we need them to satisfy. Okay. Even though the language looks a bit complicated, you can instantiate them.
I see. And do you think this NISC primitive can be replaced with some weaker primitive, maybe? Like...
Right. That is a great question. So for a single receiver, yes. For multiple receivers, no. Maybe I can tell you why. So for the single receiver, I can go up okay. So for the single receiver, you could do something very different. You could just not have a CRS at all, and you could use like a NIWI, for example, or a NIWI, for example. You could use some CCA secure scheme and decrypt the proof that you know either a signature on this message by the sender or a signature on the message by the receiver. If you imagine that the sender has a signer keeper and the receiver also. Yeah. And this would be, but for the case of MDVS, I really don't know, and I would be a bit surprised if you could do it. Because in a way, that's exactly what you're doing, is you're like proving, I mean, a signature being valid proves that either the signer signed it or the verifier signed it. Like, it does not seem clear that you can get around that.
Yeah, okay.
So maybe there is some scheme that will allow to prove this or somehow, but I think in the end, you will need somehow to do it, like to prove an OR statement for the single case. For the other, the statement is a bit more complicated. But yeah, essentially just try to map the notions into relations in the simplest way possible.
Okay.
Yeah. But yeah, that is a good question. And yeah, okay, so actually, yes, this was the last slide. So we just, yeah, we can end here. I mean, if you're very curious, we can also look at the PKE-VC, but this will take some time. So yeah.